Yo, welcome back to the NucleoGenesis project. My name is Dr. James Utley, and I am your resident codebreaker data scraper, and we are on part 8. Can you believe it already? All right, so if you don't know what nucleogenesis is, it is a temporal framework for eukaryotic nuclear blueprint archive and reconstruction. So two fractions. One is testing right away. The next is embedding the material in a dry blood spot card for future analysis. And go back and watch the other videos for sure. For sure. Okay, so we are here at section 2.6, which is system architecture. So the system architecture of the Nucleosampler. So that's one of the application that it's part of implementing a layered system that is designed to support the verifiable low latency management of temporally coupled biological samples. So taking that information, cryptographically housing it for analysis now, building a base layer of data for then analysis in the future. So each layer is responsible for a distinct case of concerns, collectively ensuring the correctness, traceability, and long-term usability of the sample data, or the to prove to collect. So because we're building this nuclear blueprint manifest, this NBM. All right. So what is it, right? So it has different layers, right? So this is like a meta. This is the meta of the meta layers, which is the presentation layer, which is an user interface that provides the primary interaction surface points at the point of collection and downstream handling. So it's like a time. It does time stamping, runtime input validation, enforces a correct schema, prevents malformed acquisition events, invalid timestamps, etc., etc. And by doing that, it constructs, kind of user interface or a boundary that reduces the downstream errors, that ensures that all the recorded events are systematically and semantically valid at the point of entry. So just kind of like that's the presentation layer is for the Nucleosampler application. Part of nucleogenesis is that it makes sure that everything's good on the intake. All right. So we have the business logic layer, which will probably change the name. I don't actually like that now. I don't like that name now. The business logic layer implements the core acquisition of nucleogenesis and really does the partitioning of the dual fractions, right? And so it gives you kind of protects it in a cryptographic wrapper, as well as it develops all the eligibility rules. So this has to meet this, or this will happen, and if this doesn't meet this, then it's invalid. And then you have the persistent layer, right, which is all acquisition events, fraction records, audit entries, and persistent locally. It's using an indexed database that is assessed through an abstraction layer. This persistent layer incorporates cryptographic verification for write and read time, ensuring that stored records remain internally consistent, tamper evident, all of that stuff, because you don't know what's going to happen in the future. And if you have it that way, then you don't have to trust another human being or potentially another AI. So it can move into different environments. All right. So beyond the architectural separation, this is a system that provides formal operational guarantees that is directly relevant to scientific reproducibility and audit tracing. So, and that's the whole process is just making sure that you have an intake that it keeps all the data that is verified, auditable, and everything for the future, and it provides some consistency. You always know what's available, the durability of the data, right? So it's not going to change from the base layer, right? You're just only going to build on it. So it's going to build this framework, and then hopefully like you'll be able to these linkages, which means like using AI models, or I guess machine learning predictive capabilities, will kind of fill in the gaps as long as you have a base layer of data. The other thing is that some of these records could be used to train other models that maybe for your own use case. I don't know. But together, this architecture ensures that the Nucleosampler functions not merely as a user interface, because it does have a UI, but as a formally constrained provenance preserving system. Like that's ultimately what it is. And it's integrate by integrating cryptographic integrity checks, hopefully on the blockchain or something that's be a public blockchain that can be audited, or immutable and audited. Workflow semantics, and the durable local persistence. The platform provides a reliable foundation for long-term horizon biological archiving. And so when you're pairing it with the nuclear reconstruction from an actual biological specimen, meaning the long horizon one, which means the dry blood spot, then it'll have some syncing. This is building a data integrity model, right? And it is it's a provenance preserving system. And by having that standard of data that's made for nucleogenesis, as I mentioned before, that data can be used for your own personal use to train other models. If we ever move into this world of personal AI, where we're using AI in health, like that information, it's all about the data for the algorithms, and that would be an important endeavor. All right, so moving on, we're now at phase two, which is the third section, right? And it's a tiered data integration and blueprint synthesis. Okay, so this is like starting to get into the meat of this thing, right? Which is the Nucleo Builder application. So we went through kind of a grand overview. Then we went into Nucleosampler, which is the integrity and prudence system builder, right? And then now we're actually building the stuff that the dreams are made of, right? But anyway, we'll get to that next time. So this is part 8, and thanks for joining, and I'll see you in the future. Peace.